Okay, so let's move on. So I hope you're convinced that we should regulate, because the laissez-faire, the equilibrium is inefficient, so we should try to get a little bit closer to the first best outcome. The problem that if you regulate with very simple regulations like an emission cap for each polluter, you cannot implement the first best. Why? Because in general, the cap shouldn't be different from one polluter to another one. Because not only they have different abatement costs as last week we had in our model, but also they impact differently pollution and different victims of pollution differently. So therefore the cap should depends on the abatement cost, or the transfer coefficient, and also the damage, marginal damage, and so on, as you can see in the first order condition for the first best. So you can have different emission caps, an upper bound on emission, which is different for each source of pollution. But then another problem also, one problem is to compute this cap. It's not clear how it's difficult. You need a lot of information about the diffusion of emission, about also in addition to the marginal damage and the marginal abatement cost, or the damage function. And also there's another issue that it's difficult to implement, because you have to measure and control and enforce this cap. And for the non-point source of pollution, fertilizer and pesticides, is quite difficult. Because you will have to measure on different places, and it's quite costly. So that's why many of those pollutions are regulated with other instruments. Like the idea of have an instrument which is related to the emission, but more easy to monitor. And one thing could be, for instance, to tax pesticide. So you want to reduce the use of pesticide, for instance, with fertilizer. So you tax them, or you ban some very polluting pesticide. So you don't regulate, the use of pesticide, or how pesticide or the chemical on the pesticide are polluting water, but the input itself through tax or ban of some chemical or some pesticide and so on. So also you can, as you know, local air pollution and water pollution is often regulated with a cap on pollution concentration. If you think about local pollution in cities like particulate matters, there's a cap that which should not be exceeded, even though if it exceeds in many cases, but then it is in the headline of newspapers. So for instance, in France, we had very warm and warm weather in April without wind, and many cities have exceeded the cap of emissions or pollution concentration for particulate matters. Especially in Paris, it happened a full week. So at the beginning, they didn't do anything, saying that, well, so they complained about, problem in France is diesel. There is a tax reduction for diesel gas, and therefore car manufacturers have developed a lot of diesel engine, so they have a comparative advantage of diesel engine, and we have a lot of diesel cars. And those are maybe good for climate change, but very bad for local pollution like particulate matters. They emit a lot of small particulates that are damaging health, and especially for people who are allergic of people who are asthma and so on. So during this week they were complaining a lot about that. But then they didn't do anything. At one point, they decided to provide public transportation for free. Well, there's a cost of that, of course, but they also, something I recommend. They recommend not to do any sport outside. But on the other hand, they recommend to take your bicycle instead of your car. So that's something is not very consistent. If you take your bicycle, of course, you reduce the emissions, but it could be bad for your health because you do some sport and you inhalate those particulates. So that's, but at one point, what they did, at the end, for one day, they banned cars with, depending on the plate number. The odd numbers were forbidden to enter Paris, something like that. But they did it for one day, and then they gave up. Okay, so that's also, so that's just to show that this type of regulation is difficult, and there is no, miracle that is. It's not magic. You will not implement the first best. The question is how far you are from the first best. What about emission fees? How could you implement the first best with emission fees? So you can have a Pigouvian approach that is tax emissions according to the marginal damage times the transfer coefficient at the first best. So this will be the Pigouvian tax. But that will imply that you will have different taxation depending on the source, and for the same reason that before, the taxation rate will depend on transfer coefficient and marginal damage, so it's quite difficult to compute. So you need a lot of information. And you need also to observe emission at the non-point source. And for same reason as I mentioned before, it's quite difficult to measure emission, how much pesticides are used within the land by farmers. Okay, so you can of course set a uniform tax on emissions, but then you don't implement the first best. So for instance, this is an example here in which so you suppose you have two polluters, 1 and 2. So let me make a picture. So consider two independent, two problems, 2 polluters and 2 victims or receptors of pollution, and the pollution goes from each polluter to each victim. And assume that they have the 2 polluters are identical in terms of marginal cost. The difference are about the victim. So one have higher marginal damage compared to the other one. The first bill will require to tax more the polluter 2 than polluter 1 because due to the higher marginal damage of victim 2. The problem that polluter 2 has a higher marginal damage on the victims than polluter 1. If you get a uniform tax, okay, then what you get, as we have seen last week, that firm will equalize the marginal abatement tax to the tax rate, and that will be the level of emission for both firms. So firm 1 will under-emit, while firm 2 will over-emit, and then you get some welfare loss. Okay. So the same story last week. There is some loss due to uniform tax rate. Okay. Now, cap and trade. So economists love markets, so they want to set markets everywhere. So the problem, an economist would tell you that the problem here, the lack of property rights on externalities like pollutions. So let's assign property right on externalities. Now the question is, would you assign property rights on emission or on pollution? You can do either way. Here, you can, for instance, assign a permit on ambient pollution at each receptor of pollution, for each victim of pollution. So you divide ambient pollution into caps. So I denote Lij is pollution rights in J. Okay. And capital Lij is the initial endowment. So what you do, you divide, you have some optimal level of pollution at J, and you divide it with endowment, so you give each polluter a share of this cap on, ambient pollution for each location. So a cap of, let's say, sulfur on water in different places, along a river, for instance. Now, what will happen if you do that? And if you allow polluter to exchange his right. So as a polluter, you can sell sulfur rights for each of the location you are polluting. But then you have to compute, so then each polluter will solve this program. So the polluter will decide on the level of emission and also on the rights that he will own in each receptor of its own pollution at each location or in which you have a market for, pollution, ambient pollution. So here you have the difference between the endowment he gets from the right he gets in each location and the final, right he gets. So then the idea is that each polluter can buy or sell this difference. This is an equilibrium price of rights, pollution rights at each receptor of pollution, and it is exogenous for polluters. Polluters are price takers by assumption. And so the polluter should care about that at for each receptor of its own pollution. And there is this constraint, which is that it should own rights on pollution concentration at each receptor. And that has an impact on the amount of emission the amount of emission he could emit. So remember that. So Lij is alpha IJL emission. So the polluter has to take into account that every time he emits 1 unit of emission, 1 unit, alpha Ij end up into the spot J. So he will have to buy Lij over alpha divided by alpha Ij rights in spot J from the market, allowances in spot J for each unit of emission emitted. Right? So this is one way to introduce a capped trade system. You set cap at different locations for each receptor of the pollution. So let's take an example here, for instance. So 2 firms are impacting some lake But for each unit of emission by 1, each unit of sulfur ends up in the lake, but only 1/2 of emission emitted by 2 ends up in the lake, okay? Because maybe 2 is more far away, or there is some water dilution along the way. So then you set a cap on the sulfur concentration in the lake, and some right on those amount of sulfur among the two. So then for 1 it's quite easy, like every time 1 is emitting 1 ton of sulfur, he has to buy 1 ton of right here. But for 2 that's different. For every time 1 emits 1 more ton of sulfur, he has only to buy 1/2 tons. Okay, that's why you have the division by the transfer coefficient. Now, if you implement this cap and trace system at each receptor of pollution, each polluter will solve this problem, and if you solve this, then you get those fourth order conditions. That is, equalize of marginal abatement cost divided by the transfer coefficient to the price of allowances in each spot J. An implication of this fourth order condition is for each spot J, you get what? You get the modified equimarginal principle. So here, for instance, you will get that minus C prime E1 equal to minus C prime 2 E2 divided by 1/2. Will be equal to the price of allowances at this spot. Okay? So then you get the first best here. Now if you want to derive the price here in this model, you have to use this market clearing condition. That is, the amount of allowance that are booked or that are owned by each polluter should be equal to the initial endowment in total. And that supply equal demand condition makes sure that you don't exceed the first best level of pollution concentration. Okay, so in theory, you could implement the first best by setting emission allowances at each receptor, measuring the allowances, asking each polluter to own, the amount of pollution that is originated from itself and that will end up into this pot. And then you will get the first best. The problem is not easy to implement, because you need some information about the transfer coefficient, about the trade here, and there's some, it's not clear, the link between the pollution concentration and the amount of allowance each polluter owns and the amount of emission. Another problem that is not in the model is the problem of market thinness. So for water pollution, for instance, it's often the case that there are very few polluters. So the market is very thin. If the market is thin, the assumption of price taker firms is unlikely, because it's more likely that there is a big firm, and those big firms will take into account the impact of their position on the market, their selling and trading strategies on prices. So then you will have market power, and if you have market power, you won't have any more first best. You will have some distortion. Okay. So it's not clear when you have distortion, it's not clear that it's better than another instrument. So you have to take into account these market thinness and market power when you compare this cap and trade system to, let's say, a tax system or a non-tradable cap, for instance. Now another way to design a type of cap and trade system is to have some exchange of emission at the source. So instead of defining allowances here, you allow the two firms to exchange emission rights. So you cap total emission, but they can exchange emission right. But then you have to take into account the transfer coefficient. That is, agent 1, for instance, could decide to emit so you have a cap system with cap on emissions. So you have cap E1 and the cap E2. You can have the same cap, for instance. But then you allow firms to exchange exchange rights. That is, for instance, agent 1 can pay firm 1 can pay firm 2 for reducing emission more than the cap. But take into account the transfer coefficient. So you get the same total cap. The idea here is to have the same overall cap, but but also same abatement cost. So the same cap at the lowest abatement cost. And to do that, what you can do, suppose that firm 1 has higher cost to abate. So what firm 1 can do is to say, okay, I will emit one more unit than the cap, but you compensate by emitting less than the cap. But the problem that is that you have to take into account transfer coefficient to have this kind of agreement. So for every time polluter 1 emits one more unit, polluter 2 have to reduce emission by 2. Okay. So you can have this kind of trade of emission rights, but with some exchange rate. The exchange rate will tell you from how much emission by 1 worth emission by 2. And that should be implemented by the regulator. The regulator should tell each firm that, okay, you can exchange this right, but every time you emit one more unit, you have to buy 2 units. The other firm has to reduce emission by 2 units. So you have to compensate the other firm from reducing the emission by 2 units. So this is one way to create a market at the source. But then again, it's quite difficult because you have to compute this, tradable right, so the exchange right among firms. Last regulation, an ambient tax. So here the idea comes to from the fact that what matters is ambient pollution concentration. And there are several polluters that are affecting this pollution concentration, and the pollution is accumulating and the damage is convex. So therefore, the optimal level of pollution concentration depends on the emission of many polluters. So one way to get something which is close to the first base is to make every polluter responsible for making any polluter realize that they are making the tax depending on the pollution of not only one polluter but several polluters. And this is the idea of this ambient tax. So it has been proposed by Segerson in a JIM paper. The idea is to define a cutoff on ambient pollution. That is, for instance, the first best level of pollution. And then compute the following tax rate. You measure total pollution. If total pollution is lower than the cutoff, then you give a subsidy to each polluter, which can depend on the identity of polluter, different subsidies, for each unit of pollution below the cutoff, this threshold. So you subsidize pollution reduction compared to this threshold. If pollution is higher than the threshold, then you tax each unit of pollution higher than the threshold, and also you can also include some fixed penalty from exceeding the threshold. What is going to be shown is shown by Segerson that you can implement the first best when there is a tax or subsidy per unit of pollution and the penalty are properly computed. Okay, I'm not doing that, but you can have a look on the paper. Okay, and the idea is to, you know, the idea in this scheme also is to make taxation depending not only on your own emissions, but also on the emission of others. Because remember, when you in the pollution concentration, you have the emission of all, you know, polluters. Okay. So it's a tax scheme which depends on what the others are doing, not only on your own behavior, but the behavior of others. In practice, it does, as far as I know, it has not been implemented for several reasons. One is because it's discriminatory taxation. You have different tax rate for different polluters, and also the tax rate will depend on total pollution, so the behavior of others. So two reasons why it could violate some legal rules. You need some information about, you know, to compute the tax rate as before. You need to know the transfer coefficient, abatement cost, and so on. And also something which is clear in the paper, that it is not budget balanced. That is, in general, it is costly. There's some cost. Okay. So you need some fund to implement this. The tax is not uniform. It is indexed by the identity of pollutant. So, I mean, if you look at the paper, she has the first part in which they have same transfer coefficient for all pollutants. Yeah. So then you have the same tax rate. And then if you have different transfer coefficient and different abatement cost, you have different tax rate. And then what happened in equilibrium, I think they match the cutoff or something. Yeah. So that's the story, you know. We are polluting some place. The regulator tells you, okay, there's some this cutoff, this threshold level of pollution. Yeah. If we exceed this threshold, we will have to pay a tax for each unit exceeding this threshold. And this tax can be different. You maybe have to pay more per unit of pollution exceeding this cutoff. This is this part. In addition, you have to pay some penalty. And we all have to pay some penalty. So you can see that there's a prisoner dilemma story, you know. We have to make some effort to reduce pollution in this place, but I don't control your emission. So if I reduce my, you know, emission, you can exceed your pollute more. And then we together can exceed this threshold in this way. Oh yeah. P is pollution here. So it's only one receptor here. So it's the J story. You know. There's one receptor. This is the story here. You care about pollution here, and there are several polluters. You set a threshold here, and if you exceed the threshold, then they have to pay a tax, and the tax depends on the identity of the polluter, plus this penalty, which depends on the identity. If the pollution concentration here is lower than the threshold, they get the subsidy for each level of concentration. So it's very, you know, collective scheme. Yeah.
That's a bit complicated. I don't know. You can ask.
You want? Yeah, so the difference is 10.
Yeah, it's 10.
And you charge, let's say, €1 to Firm 1 per unit from the 10th unit. So in total, Firm 1 pay 10. You charge Firm 2 €0.50 per unit. So Firm 2 has to pay 5. And that's how it works. And in addition, you can have also a fixed fee. Yeah. So Again, you compute a cutout, and the test is whether pollution concentration is higher and lower. If it's higher, everybody has to pay for each unit exceeding, but the price can differ, the tax can differ, plus some penalty. The tax rate would depend on the transition coefficient.
But let's say you implement an equal tax rate for everyone. And in an ideal world, you say, okay, the only thing I'm going to tax you, everyone I'm going to tax you equal if the level exceeds this level.
Yeah.
And you ensure that this is going to stay this way for 20 years. Won't you sort of expect the firms themselves to make a market and start monitoring the other firms and stuff?
Well, that's fine for me.
Yeah, exactly. That's what I'm saying. That in some way, if you can really enforce this, you solve the problem, right? The problem is no longer the social planners, but the firms.
You know, you can always expect that the cost theorem will hold. So they will coordinate emission and maybe pay some compensation and so on.
Yeah. That they say, okay, it's better that I pay you to install this because you're closer and then I can emit twice as much.
Yeah, that will be what will happen if they cooperate, cooperate outcome. So you can take the form of market, but it could put also some direct contracting. So they can go together and say, okay, so we are paying this tax because we are exceeding the threshold. Let's make an agreement about how much we should reduce emission. Maybe one firm will say, okay, well, it's very costly for me, so you have to pay me something. And but it's possible. Because they are in the same boat, I mean, regarding to this pollution. So that's why it's interesting to see what kind of incentive there are in this kind of ambient tax. That's why I'm talking about this experiment. So there has been some experiment that's been being launched by a couple. No, it's not the only one, but there are a couple of papers in which they have experimented this ambient tax pollution. See how these shape incentives for people. I just mentioned one of those experiments. It's a paper published in Environmental and Resource Economics, in which a couple of students from Strasbourg were playing a game, which is a contribution to public bad game. So it's like this game, but same transfer coefficient for all. It's completely symmetric. And also, no, not really this game, because polluters are also victims of pollution. So the story is that they are each subject has this payoff, which depends on his or her own emission. The function f is quadratic. So the more you emit, the higher is the f. But then it depends also on total emission. So the more you emit, the lower is total emission, and total emission depends, of course, on the emission order. Okay, so this is the damage side, and this is the it's the benefit side, which is something which is the individual side. Okay, so that will be the unregulated framework. Unregulated, they have to choose about the level of contribution to the public bad. The more they contribute to the public bad, the higher is the individual payoff, but the lower is the collective damage. They were matched with a group of 4 subjects, and they played different treatments or games. The first game in which they pair uncontrolled framework. There is no regulation. So then you can, in their choice of variable, the dominant strategy was to play 18 units. So X, the Nash equilibrium dominant strategy without regulation was to play X equals 18. So total pollution will be 18 for each subject times the number of players, 72 in total. If you think about efficiency, if you want to equalize the payoff, the total payoff, and therefore the payoff of individual subject, they should play 13. So reduce x from 18 to 13. And then you get some...
But it depends on the magnitude of delta.
So on the?
On the magnitude of delta.
Yeah, and also on the f function. So f function is quadratic with some parameter alpha and beta. If you have a look on the paper, you will have the value of this parameter. It turns out that with those values, these are the equilibrium, and this is the first best. Okay, so I refer you to the paper if you want. I didn't put the value here. But of course, it depends on the parameters. Now, what about the regulation? So they have designed an ambient tax in which the cutoff is the first best emissions. It's based on the first best emissions, and therefore the cutoff is the first best pollution concentration, the individual emission multiplied by the number of subjects. And they have considered 4 treatments. So the no regulation case, a flat tax per unit of pollution. So you tax each subject a constant unit of pollution. An ambient tax à la Segerson, so that is an ambient tax with a subsidy by unit of emission lower than the cutoff, so the same kind of the Segerson ambient cost. And finally, a fine applied to any subject if total emission is higher than the cutoff, than the first best. So in total, if they emit more than 52, they have to pay they have to pay something, a fixed fee. So no regulation, a constant tax rate, you tax individual emission, same way, a Segerson tax scheme, and a fine for exceeding the cutoff. Here is the result of this experiment. So they had the different groups. Each group have played one of the 4 treatments 20 times. And here you have the total pollution on average for each group of 4 people. So this is a Nash equilibrium. The unregulated treatment. So the Nash equilibrium is 72, it's here. And this is an unregulated treatment, so they are quite close to the Nash equilibrium when there is no regulation. Right? So you can see that they play quite non-cooperatively in this game. Now, what about the regulations? So this is a flat tax, all regulations were designed to give incentive to get the first best. So here the first best was 52. You can see that the tax per unit of emission and the ambient tax, the tax per unit emission and also the penalty for exceeding the tax. So these two are close to the first best. So you have something which is close to the first best across time with those 2 regulations. But the ambient tax, that is the Segerson regulation, lead to lower emission compared to the first best. And what is the reason for that? What did you guess? Remember what was the shape?
You get something back if you emit?
You get something back if you emit less than the threshold. So this part. So that's why people tend to emit less than the threshold.
Kind of subsidy, right?
Yeah, subsidy. The subsidy. Yeah, exactly. Yeah. Whereas for instance, for the fine for exceeding, you get the fine only if you exceed and nothing below. That's why people want to match to the first best. And with the constant tax, they just find the first best. And you can see when you compute the individual strategy for people. So here you have the frequency of each individual strategy. Whether people play 1, 2, 3, 4, up to 20. So most of them, in the unregulated case, play the Nash strategy. Some of them play higher, some of them play the maximum amount 20, but very few play, for instance, very few play the first best, if they are not regulated. With a flat tax, you have a lot that are playing the first bet and some distribution around the first best. Interesting.
No one is playing 20.
And no one is paying 20 now. And no one playing non-cooperatively because they will have to pay more tax. So they can find something which is, they are really around the incentive, what the incentive provides to play 13. And the treatment, you can see that with the ambient tax, there is a huge distribution here. Because people want to get the subsidies from people. And, the problem in this ambient tax, there is some asymmetric Nash equilibrium also, in which some people play quite high, but if you expect the other one to pay, to play those strategy, then of course you are incentive to play a lot, to respond by, emitting a lot, because you so know that you will just go below the threshold. So that's why you have like a huge distribution. And it's costly because you have to pay the subsidy to those people also. So there's a cost on that. And now for the treatment with the fixed fine, if you exceed the cutoff, you have also some distribution here, but mostly around just here. Very few are playing dangerous strategy, because if you play something, you have very high chance to be above the cutoff. Whereas here you have lower chance. Some are very prudent; they want to play something to be sure to be below the cutoff. Okay? So that's why at the end you get something which is close to the first bet here, but here you get something which is lot of variation of what's happening. Remember, not only you get something which is below the first, but also a lot of variability across time. Okay, let me conclude the lecture for today, and then after the break we will have a look on the problems. The question today was to how to regulate the non-point source pollution. To answer this question, I provided the model, and the model tells you that the regulation to take into account pollution diffusion through the transfer coefficient. Out of the model, we get this modified equimarginal principle that take account for the transfer coefficient. If you have a uniform emission cap or emission fee, you don't have something efficient. You should have heterogeneous cap or fees. You can imagine a cap and trade system, either for pollution concentration or for emissions, but it will be quite complex. For instance, if you have a cap and trade system for emission, you should have a trade ratio that tells you for how much each polluter could exchange its own emission reduction with another polluters. And then I also talk about this ambient tax and subsidy scheme, which will be one way to get something efficient, but the thing is, as you can see in the experiment, it does not always implement the first best.